all these objects move together, which means they all have the same acceleration. Finding the weight of the whole string, we have to find the weight of only that portion, and the tension is acting in the vertically downward direction, only the component of the tension. The last class we talked about one of the forces called a normal reaction. Here we'll talk about the next force called a tension force. See, we will restrict ourselves only to tension in a string. Things like a pulley block system and other complicated things will be done later in the next class. Here we will do simple things related to tension in a string. What is a tension force or tension in a string? Take a string, okay, this is inextensible string. So the length of the string cannot be extended any further. That is the maximum length. But you try to extend this, applying a force. Now there is an inbuilt mechanism in the string that will prevent the string from getting stretched any further, right? So this hand is trying to apply a force in the opposite direction, trying to stretch the string. So this tension is in this opposite direction, right? So there is a force due to the string in the opposite direction which will try to prevent the string from getting stretched. Alright, now on the other hand, you take this point. At this point, the force is applied by the hand in this direction. So the tension will be acting in the opposite direction. So the tension may have different directions at different points. At this point, the tension is in this direction. At this point, tension is in this direction. But the tension will always try to prevent the string from getting stretched because the length of the string is fixed. Take for example, see this block. Okay, this is hanging in the string, right, vertically downwards. What are the forces acting on this block? Obviously, the gravitational force is acting on this block in the downward direction, right? Yes. Now, against this gravitational force, the tension is acting in the opposite direction because this gravitational force is trying to stretch the string in the downward direction. So the tension will be in the opposite direction, upward direction, right? So these two forces balance each other because the object is in equilibrium. So that means the downward gravitational force is balanced by the tension force in the upward direction. So these two forces are equal in magnitude but opposite in direction, right? So you take this example. This guy is trying to stop the car from moving using a rope. The car is trying to move in the forward direction, but it is stopped by a force. What is the force that is stopping this car from moving?
Force applied by the person.
No, the person is not applying a force on the car directly. He applies a force on the rope only. In turn, the rope applies a force on the car. That force is what we call by the name tension. Right? So the tension force is what is stopping the car from moving, right? Yes. Now, as long as this rope is slack like this, there is no tension force. The tension on the rope is zero. Now, when it becomes taut like this, so when it is stretched, it becomes taut, then the tension starts acting on the car, right? So the car is moving with some acceleration in the forward direction. Now a force, tension force, is acting in the backward direction. So these forces balance each other. That is why the car is not moving. So that is in equilibrium. Do you understand? So the tension force is the force acting on the car in the opposite direction to prevent it from moving. You understand? So that is tension force on the rope. Okay? Yes. Now we have two types of strings. One is an ideal string which is massless. Nothing as such is massless, but the mass of the string is negligible compared to the other objects in the context. So that is a massless string. For a massless string, the tension is same at all the points on the string. Okay, at any point you find the tension, so that will have the same magnitude. But the directions may be different at different points depending upon the other forces, but the magnitude of the tension at any point on the string, so that has the same value, right? So that is a massless string. We also have the other type of string, so a string with mass, right? A string which has some significant amount of mass. So for that string, the tension may be different at different points because the string itself has some mass, so that may contribute to the tension on the string. So that means there are two types of strings, but in most of our questions we will only consider strings without mass, right? A massless string only. So we can take the tension to be same at all the points on the string. There are a very few questions which has a string with mass, right? A very few questions, but in most of the cases we will have a string without mass, right? So that means you can take the tension to be same at all the points on the string. Okay, yes. So these are the only points that you have to know about the tension for now, right? Because in this class, as I told you, we are only going to talk about tension in a string. So pulley block related things will be done later. Now let us use all these basic concepts to solve some questions based on the tension in a string. Okay. A string of mass m and length L is hanging vertically. The tension x meter below the point of suspension is. Here we have a string or a rope which has some mass. It is not a massless string. So that means the tension will be different at different points on the string. We have to find the tension at a particular point x meter below the point of suspension, right? At that particular point, what is the tension? You tell me what is the reason for this tension? At a point on this string, so there is a tension. So what is the cause of this tension? What creates this tension?
Mass of the lower part of the string?
Yes, the mass of the part of the string below that point, that mass is trying to pull this string downwards. There is a resistance force in the upward direction, right? So that resistance force is the tension, right? So let us find the mass of the portion of the string below that point. Okay, we have the total mass, so that is capital M, and the length of the string is also known capital L. Now we have to find the mass of that portion. So the mass is proportional to the length, because the mass is distributed uniformly, right? This is a uniform string. That means the mass is distributed uniformly. The mass is proportional to the length of the string, right? Yes, now let us find the ratio of the mass to length, right? So the total mass is capital M. So this is the total mass divided by the total length, right? That is L. This ratio is same for that part of the string also, right? So that part has mass M divided by the length of that portion. So the total length is L minus X, right? L minus X is the part of the string below that point. So that is the length L minus X. Okay, so that will give you the mass of the required part of the string. So that is, yes, so M equals, so capital M divided by L multiplied by L minus X. So we've got the mass, right? So at that point, let us use our Newton's law, right? Yes. Now what are the forces acting at that point? So that is the gravitational force, right? So the weight of the object, right, due to the string, right, below that point. So that has mass, this one. And mg is the force in the downward direction. And there is a tension in the upward direction. So that means the total force acting at that point. So tension in the upward direction minus mg in the downward direction. So that must be equal to 0, right? So at that point, no acceleration. So 0 or T minus mg is 0. Now we can substitute this value of m to get the tension. That's all, right? So our required T equals mg. But m is found here. So that is m divided by L minus x multiplied by g. So that's all. So that is our required answer. So the tension. So the tension is dependent on x. See, as a particular case, suppose x is L itself. X is L itself. That means L meter below the point of suspension. That means the bottommost point, what is the tension? 0, right? So because there is no mass below that bottom point, right? So that means the tension is 0 at the bottommost point. But if you take x as 0, which means the topmost point, so that will have tension mg. That means the maximum tension is at the topmost point. The minimum tension, that is 0 at the bottommost point. So in between we have tension, which is a variable, right? So tension at different points on the string. So the tension is different at different points on the string. So this is the general formula for the tension at various points on the string, right? So that is the answer. A string of mass m attached to a block of mass capital M is pulled by a force F in the horizontal direction. The tension at the midpoint of the string is. Here, a string attached to a block is pulled horizontally by a force F. We have to find the tension at the midpoint of the string. So here also we have a string which has some mass. That means the tension is not same at all the points on the string. At different points we have tension having different values. Now at the midpoint we have to find the tension. So what do we have to do? So what are the forces acting on the system? Let us consider the block and the string as one system, right? So this is one object. Now we have a force F acting on the block only in the horizontal direction. Let us consider this as a system. So the block and the string together. What are the forces acting on the system in the horizontal direction? The only force is the force F, right? So F is the only force acting in the horizontal direction. So F, that equals, by Newton's second law, mass times the acceleration. But what is the mass? So the mass of the block is given and the mass of the string is also given, the total mass. So that is capital M plus small m, which is mass of the string. So that is the total mass multiplied by the acceleration. Okay, so that's all. So this is the relation. Okay, now for this system, now we have to find the tension at the midpoint of the string. Now this time we consider this system having the block and one half of the string, only this portion on the left, right? This half of the string and also this block, that you consider as one system. You tell me, what are the forces acting on this system now?
The same force F?
No, this time the force F is not directly acting on the block and this half of the string. The force F is acting directly on that part of the string only, right? That half on the right. Now we have to find the force acting on the block and this left half of the string. So that is the tension force, right? At that midpoint we have a tension which is pulling this block and this half of the string in the horizontal direction, right? The tension at that point, okay? The tension is the only force because the force F acts only on that part of the string, okay? So what are the forces here now? Only the tension, right? So tension is the force acting on that. So now we have considered the block and the half of the string, the string on the left, right? So the left half of the string only, okay? It is understood. Now what are the forces? The only force is the tension at that point, the midpoint. So tension is the only force. So tension equals mass times the acceleration. But what is the mass? So we've considered only this part, the block and one half of the string. So the block has mass m and one half of the string, so that has mass m divided by 2. So this is the total mass multiplied by the acceleration. But what is the acceleration? The acceleration is same as in this case, right? So in this case we have acceleration. So because all these objects, right, the block and the string, all these objects move together, which means they have the same acceleration. So whatever is the acceleration in this case, same acceleration here also. So that means this multiplied by a. So that's all. So we've got the tension, right? But this a can be substituted from this. So that is our required answer. That's all, right? So that means our required answer here is m plus m by 2 multiplied by this acceleration that can be substituted from this. So F divided by m plus m. Okay, so that's all. So that is our required answer. If you want, you can simplify this. This is 2m plus m divided by m plus m multiplied by F by 2. So that's all. So this is our required tension at the midpoint of the string. Okay, so that is our required answer. A string of mass m and length L is hanging from a point A. Its linear mass density varies with the distance x below the point A as k times x. The tension at a distance x units below the point A is. This question is similar to the other question we have done. So a string is hanging vertically down. We have to find the tension at a point x meter below the point of suspension, right? But here the difference is this string is not uniform. The mass is not distributed uniformly over its length. At different points, the linear mass density is different, right? What is the relation between mass and the linear mass density? We have the formula, right? Linear mass density. So this is linear mass density. So that has formula. So lambda, linear mass density, equals, that is the mass of the object divided by the length, right? Mass divided by the length, that is the linear mass density. But this lambda is not a constant here, right? So let us consider, so obviously for questions of this type we have to use integration, right? You consider a small portion of this ring, of this string, so x meter below that, which has length only dx. So because dx is very small, so in that portion we can consider the linear mass density to be constant. Okay, so only length dx. Now what is the mass of that portion? So the mass of that portion, so generally the formula is mass equals, right, lambda multiplied by L. Okay, yes. Now for that particular portion, okay, only that small portion, the mass is taken as dm, because only that small elemental portion, so we have taken the mass dm. So dm equals lambda. But what is lambda? So that is given, it is dependent on x, so kx. So that is linear mass density multiplied by the length. But the length is what? So that is dx. Dx is the length of that portion of the string. So that is dx, kx multiplied by dx. So we have got the mass of that part. We will find the tension only due to this mass, not the entire string, only due to the portion of the string, so dm. So that mass has a, what is the weight of that? So that is mass multiplied by the g, right? So dm multiplied by g, that is the weight, and tension is in the opposite direction. So what is the total, the mass, right? So what is the tension due to only that small portion? Okay, the tension due to only that small portion, say dx, only dx. So due to that small portion, what is the tension? So that is taken as dt. Again it is elemental to say only dt. So dt, so that dt must be equal to the weight of the object. So the weight is balanced by the tension in the upward direction. So dt must be equal to weight, or dt minus the mass is dm multiplied by g. So that equals 0. Alright, so t minus mg. But m here is dm only, so only that small portion, right? Yes. Now dt. So we found dt. Now what is dm? So that's what we found here. So kx dx multiplied by g, kx dx multiplied by g. Now we have to do integration to get the value of tension, right? So let us do the integration. So dt equals kgx dx. Let's do the integration. Okay, so initially 0 to t. At that particular point the tension is t. Now what is the range here? Okay, the limit of the integration. So x is from, yes,
from 0 to L.
No, not 0 to L. We are not finding the weight of the whole string. We have to find the weight of only that portion of the string below that point, right? We want to find the tension at that point. So the tension there is due to the weight of the string below that point only. So that means, so we don't need to consider the whole string. At that point, what is the value of x? X only, right? X meter below that point of suspension, x. And the bottommost point, the last value, so that has value of x, L. So L is the last value, and at that point the value of x is x only, right? X to L, not 0 to L. So we don't want the entire mass or the weight of the string, only that portion of the string below that point. That is the only portion that contributes to the weight at that point. Okay, so that is below. So that weight acts in the downward direction, against which we have the tension in the upward direction. Do you understand? So that's all, x to L, not 0 to L. So let us do the integration. That's it. So this is t. So that equals, so this is integration. So x square divided by 2 from x to L. So that's also, that is the answer, kg divided by 2 x square. If you substitute, L square minus x square. So that's also, this is the required tension at the point x meter below the point of suspension, right? So here the only difference is the string here is not uniformly distributed. The mass is not uniformly distributed over the length. So for that we have to use the formula of linear mass density. Okay, so we make use of integration to get this answer, right? Kg by 2 L square minus x square. The tensions in the strings given in the figure are, here 3 blocks are given which are connected by some strings. This block M3 is pulled by the force F in the horizontal direction. We have to find the tension in these 2 strings. Okay, now these tensions are not same, right? They are different because these 2 are different strings, right? They are not connected. These 2 are different strings, so the tension will be different. Okay, so let us find the tension, say T1 the first string, and similarly T2 the next string. Alright, let us find the tension. First of all, we will consider the whole thing as one system, right? All the 3 blocks put together as one system. So what is the total mass of the system? M1 plus M2 plus M3. We don't consider the mass of the string, so because it is massless, so like I told you, so we will consider all the strings henceforth to be massless. Okay, so that means tension is constant throughout its length and no mass at all. So M1 plus M2 plus M3. So all the blocks put together, what are the forces acting on this system in the horizontal direction? Only in the horizontal direction. So that is the force F only. So let us consider this system. So all the mass, okay, so M1 plus M2 plus M3. So all these put together as one system. So the only force acting on this system is F. Force equals mass times the acceleration. So that is M1 plus M2 plus M3 multiplied by acceleration. Okay, so that's it. That will give you the acceleration. If required, we can find the acceleration. So that is F divided by M1 plus M2 plus M3. Okay, yes. Now we will consider, we have to find the tension, say T2. So how to find the tension T2? Now we will consider only this as a system, M1 plus M2 only, not M3, M1 plus M2. So now what are the forces acting on this system? So the only force acting on this system is this tension T2. T2 is the only force because that is pulling in this direction. This T1 is internal now because this is a system, internal force. The only external force acting on the system is the tension T2 in the horizontal direction. So that's all. So T2. So that equals mass times the acceleration. So what is the mass here again? So M1 plus M2 multiplied by the acceleration. Same acceleration because all the blocks move together. Okay, so that's all. So this is T2. Now we have to find T1. For that we will consider only the mass M1. That's all. So what are the forces acting on only the block M1, right? So that is T1. T1 in this direction. So T1. That equals mass times acceleration. So M1 multiplied by the acceleration, that is A, right? Same acceleration. That's it. We don't need the acceleration. We want to find the T1 and T2 because the acceleration is known already, right? The acceleration equal to F divided by this. So that can be substituted to get our required value of T and T1 and T2. Okay, that's it. So if you substitute here, the value of T2 is M1 plus M2 multiplied by A. So that is m1 plus m2 multiplied by the acceleration. So the acceleration here is f divided by m1 plus m2 plus m3. So that's it, that is the tension T2. Similarly here, so m1 multiplied by A, so m1 multiplied by same thing, f divided by m1 plus m2 plus m3. So that's also, this is our required tension T1, and similarly, so this is T2, and then if acceleration is required, so that is f divided by m1 plus m2 plus m3. Okay, so that is the answer.
Can't we consider the blocks separately instead of a system?
If you don't want to consider this as a system, you want to consider all these blocks one by one, right? So that can also be done. See, that is just another way to do it, right? Alternatively, see, you want to consider the block m1. So what are the forces acting on m1? So that is the tension in this direction, right? So T1. So T1 is the only force acting on this, which means T1 equals mass times m1 multiplied by acceleration. So that is one equation. Similarly, let us consider m2. So what is m2? So T2 is acting in this direction, T1 is acting in the opposite direction. So what is the direction of this T1? See, T1, the tension itself does not have any direction, right? So it depends on which object it acts on, right? See, like this. M1, if you consider M1, tension is acting in this direction because the force is pulling this block in this direction. The tension is the only force acting on the block M1. The object is moving in this direction, so that is the direction of tension. But when you consider M2, the same T1 is acting in the opposite direction, right? So it is acting in the opposite direction because the other force T2 is the more dominant force because that is pulling this object in the forward direction. So that means this is the resistance force. Tension is a resistance force which is acting in the opposite direction. So T2 has two different directions depending upon which object it acts on, right? Yes. So M2. So one force T1, T2 is in this direction, and similarly T1 is in the opposite direction. Okay, so T2 minus T1, so that equals again mass times acceleration, so that is m2 multiplied by same acceleration. Okay, now let us consider m3. So what are the forces acting on m3? F in the forward direction, right? F in the positive direction, so F. In the opposite direction we have this tension T2, so that equals m3 multiplied by A. So these are the three equations. Now solve them, you get our required answers. How will you solve? So we have to eliminate A from all the three equations, right? So we want T2 and T1. So T1 is already found, M1A, but A is not found, right? So we have to simplify this. So what we can do, we can add these values. So just add all these equations. So we get T1 minus T1, T2 minus T2, that gets cancelled. So F equals, so if you add all this, we get M1 plus M2 plus M3 multiplied by A. Okay, so that's what that is found, acceleration. Acceleration F divided by M1 plus M2 plus M3. That acceleration can be substituted back here to get T1. Similarly here to get T2. Okay, so that can also be done. So this is also one way to do this question, considering the objects as one system. Okay, yes. So anyway, the answer here is this one. T1 is this, and T2 is also found here, M1 plus M2 F by M1 plus M2 plus M3, and the acceleration here is F divided by M1 plus M2 plus M3. So that is the answer. The block given in the figure is in equilibrium. The tensions in the strings are given by. Here two strings are attached to a block, but these strings are not horizontal or vertical. So they are making some angle theta or phi with the horizontal. Now we have to find the tension in these two strings. Okay, yes. Now this block is in equilibrium. So that means the total force acting on this block should be 0. But we will consider the total force in two different directions. One in the horizontal direction, one in the vertical direction. What are the forces acting on this block in the horizontal direction? The components of these two tensions in the horizontal direction, right? The gravitational force is acting in the vertically downward direction, but that doesn't act in the horizontal direction. The only forces are the components of these two tension forces in the horizontal direction, right? Yes. Now what is the angle made by the tension, say T2, with the horizontal alternate angle, right? Phi. So this is also phi. So T2 makes angle phi with the horizontal. That means what is its component? T2 cos phi. So that is a component in the horizontal direction, positive direction. Okay, similarly this T1 makes angle theta with the horizontal. That means T1 cos theta in the opposite direction, so minus. Okay, so that means if you consider all the forces in the horizontal direction, so let us first write the forces in the horizontal direction. Okay, in the horizontal direction, T2 cos phi, so that is in the positive direction, T2 cos phi minus, so this one, so minus T1 cos theta. That's all. This total force must be equal to 0 because this block is in equilibrium, right? So that's all. So that is one equation. Similarly, now we will write the equation in the vertical direction. So what are the forces acting in the vertical direction? Again, the components of these two tension forces in the vertically upward direction, and also we have this weight force, right? The gravitation force acting in the downward direction. Okay, so what is the component? So T2, so this angle is theta, so that means this angle is 90 minus theta. That means the component here is sine, right? Sine phi, T2 sine phi. That is the vertical component of T2, right? Vertical component of T2 is T2 sin phi. Already we have written the horizontal component T2 cos phi. So vertical component T2 sin phi. And similarly, the other one, T1. So that is plus, right? Both are in the upward direction. So T1 sin theta. Okay. So, and also we have the gravitation force acting in the downward direction, mg, right? So minus mg equal to 0. Or this equals mg. Okay, so that's all. These are the two equations. We have to solve these two equations to get the value of T2 and T1. How will you solve? It is like two equations in two variables, right? So simultaneous equations, we know how to solve it. So we have to eliminate one of these values, right? Like so let us eliminate T1. So what do? Multiply the first equation by cos theta, sin theta. Multiply the second equation by cos theta, so sin theta cos theta. So they'll cancel this equation, right? So like this. So take this as equation number 1, this is equation number 2. So multiply the first equation by sin theta, this by cos theta, and add these two equations. So what we do here is multiply the first equation by sin theta and add this with the second equation multiplied by cos theta. So what do you get? So T2, so this is multiplied by sin theta, so cos phi sin theta. And similarly, this is T2 sin phi cos theta. So what you get? So T2 multiplied by so sin theta cos phi, and added with this one. Here we multiply by cos theta. So that is cos theta sin phi. Plus, so this will become this get cancelled, right? So T1 cos theta sin theta, right? Cos theta sin theta, and here second is multiplied by cos theta, so sin theta cos theta. So that will cancel this, so that means that will become 0. So that equals, again here this is multiplied by sin theta, 0 anyway, so mg multiplied by cos theta. So this is like normal solving simultaneous equations, that's also nothing different. Okay, so that will give you the value of T2. So our required T2 equals, so mg cos theta divided by sin theta, this value you can divide sin theta cos phi plus cos theta sin phi. Isn't it like sin A cos B plus cos A sin B? So that is the formula for sin A plus B, right? So you need to know some basic trigonometry, right? Basic trigonometric identity here. Sin A cos B plus cos A sin B is sin A plus B. So this has value sin A plus B, which means theta plus phi. So that's all. That is the value of T2. Okay, so T2 is mg cos theta divided by sin theta plus phi. So we found the tension T2. Okay, similarly we can find T1. So to find T1 we have to eliminate T2. So same thing we have to do, multiply this by what? So we want to eliminate T2. Okay, so to eliminate T2 we have to multiply this by cos phi. You have to multiply this by sin phi. So then this will get cancelled. So what we have to do is, so first equation, second equation you multiply the second equation by cos phi and add subtract the first equation multiplied by sin phi. Okay, so that's all. So that will give you the answer T1 equal to, can I write directly? So you will get, you are multiplying this by cos phi, so sin theta cos phi plus cos theta sin phi. So that is same as sin A plus B again, so sin theta plus phi. So this is multiplied by cos phi, so mg cos phi. So T1 equals mg cos phi divided by same calculation, so it is sin theta plus phi. So mg cos phi sin theta plus phi. So that's all. So this is the tension on this string T1. So and this is T2. So that is the answer, right? The tension in the horizontal string given in the figure is, here we have two blocks attached to some strings. We have to find the tension on these three strings, right? So there is a string in the horizontal direction. So let's take the tension on this string to be T1. Similarly, that string over that ring, right, it's passing over that ring, so that has tension say T2, and similarly this vertical string has tension T3. Let us find the values of T1, T2 and T3 one by one. See, that string is going over that ring, right, so the tension at any point on the string remains same because it is a smooth string, right. So this ring, right, it is passing over that ring, so that does not change the tension because it can move freely over that ring, right. So the tension is same at any point on that string. So three strings are there, we have to find the tensions, right. Let us write the equation for these two blocks. Okay,
The strings are connected. Can we consider them as one string?
no, even if the strings are connected, we cannot consider them to be one string. See, consider that string passing over that ring. See, that ring does not restrict the motion of this ring. It only changes its direction. So it can move freely over that ring. That means the tension does not change. We can consider that as one single string. But that is not the case at the junction point. So where at that point where these three strings meet, at that point there is a restriction of motion, right? It is like this. There is one string. Okay, now the tension is same at every point on the string. Okay, but if you hold at some point, okay, you hold it tight at some point, now it will become two strings. Okay, now this portion is one string, that portion is another string, because the tension this time need not be same because there is a restriction. You understand? So that is the case here. At that point, junction point, so they are separated. So these three strings have different tensions. Do you understand? So we should treat them as different strings only. Okay, so that's why we've taken as T1, T2 and T3. Okay, yes. Now let us consider the, okay, so what are the forces acting on the blocks, right? Small m, right? Let us consider the forces acting on the block, say small m. Okay, so like this. So what are the forces acting? Gravitational force in the vertically downward direction, so that is mg. And the tension is acting in the opposite direction, right, against the gravitational force, so that is so T3. That is the total force, so that must be equal to 0 as the block is in equilibrium. Now we will write for the other block also, right, capital M. So what are the forces acting on this? So vertically downward direction we have the gravitational force, so mg, and also the tension force T2 is acting in the vertically upward direction, right, because T2 is same, right, the tension is same at any point on the string, right, so that means at that point the tension is acting in the upward direction, right, away from that mass, away from that point, right, opposite direction. So mg minus T2, so minus T2, so that equals 0. Okay, now we will write the total force at the point, junction point, right, at the point, okay, at the point where these three strings meet, okay, at that point. So the total force is 0, right, because that point is also in equilibrium, or the point has mass 0, right. So at that point, what are the forces acting in the vertical direction? In the vertical direction we have T3, right, vertically downward direction, and also the component of T2 in the vertically upward direction. T2 makes angle 90 minus theta with the vertical, so that means T2 sin theta, so that means T3 minus T2 sin theta, so that equals 0. So that is in the vertical direction. Similarly, horizontal direction. Horizontal direction we have the T1 in this direction. Okay, if you take this direction positive, so T1 minus the component of T2 in the horizontal direction. T2 makes angle theta only, alternate angle theta with the horizontal, so T2, yeah, T2 cos theta, so that equals 0. Okay, yes, now that's all. So these are the equations we have to solve to get the value of T1, T2, T3, right. So we have to eliminate theta, we have to get the answer in terms of alright, so m only, okay, m and capital M, that's it. So we already got the value of T2 and T3, okay, T2 is mg, T3 is again small mg, so that we can use here to get our required answer. See, so one tension T2, so that equals mg, so that is direct, and similarly T3 is also found small mg. Okay, now T1 we have to find. Okay, so here we have T1 is T2 cos theta. Okay, so T1 equals, so this is done already. Now what we need is just T1, so T1 equals T2 cos theta. Okay, so T2 cos theta, but T2 is already known. So what is T2? So that is mg. But what is the value of cos theta? So we don't know cos theta, right? So we know only, so what is sin theta? Sin theta is T3 divided by T2. So let me do it separately here. See, we know that sin theta is T3 divided by T2. But already T3 is known. So T3 divided by T2, that is small m divided by capital M. So that is mg divided by capital M. But we don't want sine theta, we want the value of cos theta. But cos theta can be written as root 1 minus sine square theta, right? The square root of 1 minus sine square theta. So that is cos theta, right? Cos square theta plus sine square theta is 1. So this equals mg multiplied by, so root 1 minus cos sine square theta. But sine theta is known, so that is square root of 1 minus sine square theta is m square divided by m square. Okay, so that's also, that is the answer. So this m will get cancelled, right? M square under root. So this is g multiplied by square root of m square minus m square. So that's all. So this is the value of our required tension T1. So these are the things required at T1, T2 and T3. So that is the required answer. The force F required to keep the blocks in equilibrium is. Here also we have two blocks connected by some strings, and a force F is acting on the block capital M in the horizontal direction. We have to find this force F so that these two blocks are in equilibrium. So obviously we have to consider all the forces acting on these two blocks, but in two different directions. Let's consider all the forces acting on the blocks in the horizontal direction, right? What are the forces? See, one of the strings is making angle theta with the vertical, the other string makes some angle phi, right? We assume that the angle is phi. Phi is the angle made by the other string with the vertical, and the two tensions, right? The tension on these two strings are taken as T1 and T2. Okay, yes. Now, so this angle is theta. That means the angle made by this string with the horizontal, that can be taken as 90 minus theta. Similarly, the other string makes angle, so 90 minus phi with the horizontal. Okay, so all these values are known. Now using that, let us find the forces acting on these blocks in these two directions, right? Horizontal and vertical. Now let us first consider the horizontal direction. What are the forces acting on these two blocks in the horizontal direction? So first of all, let's find the block capital M. Okay, what are the forces? The force F is acting in the horizontal direction, positive direction, so F, minus that component of T2 in the horizontal direction. T2 makes angle what? 90 minus phi, right? That angle is phi with the vertical, with the horizontal the angle is 90 minus phi. So that means T2 sine phi, okay? T2 sine phi minus T2 sine phi. So that is the angle, that is the total force, so that must be equal to 0. Okay, so that's all. So this is the equation of for M in the horizontal direction. Similarly, we will write for the other block M in the horizontal direction. What are the forces? The component of T2 and T1 in the horizontal direction. So T2 makes angle 90 minus phi. So T2 makes angle 90 minus phi with the horizontal. So its component is sine phi, right? So which means T2 sine phi in the positive direction. In this direction, similarly the component of T1 in the opposite direction, so minus T1 again sine theta, because that angle is 90 minus theta again. Okay, done. So this is in the horizontal direction. Similarly, we will find, okay, write the equation for the vertical direction. Now first of all, for the block say small m, right? For the block small m, so what is the value? Now what are the forces acting on the block? Component of T1 in the vertical direction, and also the gravitation force in the vertically downward direction. We also have the component of T2, okay, in the horizontal vertical direction. So what are the forces? First of all, for the block okay, let me write for the block capital M, so anyone. So what are the forces? Gravitation force in the vertically downward direction, so mg, and then the component of T2 in the vertically upward direction, that makes angle phi only, alternate angle phi, which means mg minus, okay, so T2 cos phi. So that equals 0. Okay, so this is for M. Similarly for small m, we can write again mg in the downward direction, mg, and also the component of T2. So component of T2 in the downward direction, so that is plus only because same direction. So plus T2 cos phi. Similarly, the component of T1 in the vertically upward direction, opposite direction. So that means, so minus T1 cos theta. So that equals 0. So these are the equations. Solving them, we should get the value of the required value of F, right? So F is what we need, but we have to eliminate. What are the things we have to eliminate? T2, T1, and also phi. These are the things not given in the question. So we have to eliminate T1, T2, and phi. Theta is already given in the question, so we can leave the answer in terms of theta. So let's name them. So first equation number 1, 2, 3, 4. Okay, so how will you solve them? So we have to find F, eliminating T2, T1, etc. So first, shall we add these two equations? So if you add the first two equations, first equation and second equation are added. So we'll get T2 sin phi, T2 sin phi. So that gets cancelled. So we get F minus T1 sin theta. So that equals 0. So that is one thing. Similarly, these two equations again we can add, because minus T2 cos phi plus T2 cos phi. So we can add the two equations. So third equation and fourth equation can be added. So we'll get this gets cancelled, mg plus mg. So that is capital M plus mg minus T1 cos theta equal to 0. Okay, so these are the two equations. Again we have to eliminate this T1. So T1 should be eliminated. Okay, so let's eliminate T1. So this becomes F equals T1 sin theta. So T1 sin theta, that means sin theta multiplied by T1. But T1 can be written from this. So what is T1? It is M plus mg divided by cos theta. That's all. So that is the required answer, right? So sin theta by cos theta can be written as tan theta. So that is simply M plus mg multiplied by tan theta. So that's all. So that is the required force F for these two blocks to be in equilibrium. So it's a very simple question. We consider the total forces acting on the two blocks in two different directions, horizontal and vertical. So that total force is 0. That's all. So that gives you a required answer, M plus mg tan theta. Okay. The normal reaction between the wall and the sphere of mass 6 kg and radius 5 meter given in the figure is. Here a sphere is connected to a string which makes some angle with the vertical wall. We have to find the normal reaction between the wall and the sphere, right? This sphere is in equilibrium. That means the total force acting on the sphere is 0. We have to consider all the forces acting on the sphere in these two directions, horizontal and vertical direction. What are the forces acting on this sphere in the horizontal direction? See, one is the normal reaction due to the wall. Normal reaction is acting in this direction. See, normal reaction is perpendicular to the wall, right? Surfaces perpendicular to the wall, which means that normal reaction will pass through the center of the sphere, right? So it will pass through the center. Okay. Similarly, we also have the component of the tension. The tension is along this string. The tension has a component in the horizontal direction. So these two forces act on this sphere in the horizontal direction. So let us consider these two directions, horizontal and vertical direction. So in the horizontal direction, so what are the forces acting? So the normal reaction is acting in this direction, right? So the positive direction, the normal. And then the component of the tension in the opposite direction, minus tension, and the vertical angle is taken as theta. That means this angle is 90 minus theta. So the component is sin theta. So that means the tension T multiplied by sin theta. So this is the component of the tension in the horizontal direction. So that must be equal to 0. Okay, so that is the horizontal direction. Okay, done. Now in the vertical direction. So what are the forces acting in the vertical direction? Again, the component of the tension in the vertical direction. So this angle, alternate angle. So same angle theta. T theta, right? That means cos theta. T cos theta in the vertically upward direction. So T cos theta. And also the weight in the downward direction, right? The gravitational force is acting in the downward direction. So minus mg equal to 0. So that's also, these are the two equations. Solve them to get our required value of the normal reaction. So we don't need tension. So which means the tension can be substituted here to get n. Okay. So this gives you the value of okay, from this we can get n. So n equals T sin theta, but T can be calculated from this. So mg divided by cos theta. So that is T multiplied by this sin theta. So that means we get mg tan theta. So that's all. So this is our required normal reaction. But tan theta is not known, right? So we have to find tan theta, right? That is not given. Theta is not given in the question. So we have to find tan theta. But we can consider this right angle triangle, right? See, this is a right angle triangle, right? So the length of the string, so that is given, right? 8. So 8 is the length of the string, okay? And the radius of the sphere is also given 5 units, right? That means 8 plus 5, that is the total. From the center of the sphere to that point of suspension, that is 8 plus 5, 13. 13 is the length of the hypotenuse if you consider the right angle triangle. So that is hypotenuse, which is 13. And the radius of the sphere, that means the base is 5. So we can use Pythagoras theorem to find this length, okay, which is 12, right? Square root of 13 square minus 5 square. So that is 12. So this right angle triangle is completed. That means you can find sin theta or tan theta, whatever we want. So what is tan theta? Opposite side divided by this adjacent side. So that means, so this value is mg multiplied by tan theta, right? Opposite side, that is 5 divided by 12. So that's all. So this is a required answer, but the value of m is given, right? The mass of the object is given. So that is 6 kilograms. So that can be substituted here. So this is 6 multiplied by g, you can take it as 10 multiplied by 5 by 12. So this will give you the answer. So that is 25 times 5. So that is 25 Newton. So that is our required normal reaction, right, between the wall and the sphere. So that is the answer. Two blocks of equal mass m, 2a distance apart, are connected by a string. A force F acts at the midpoint of the string in the upward direction. The acceleration of the blocks when the separation is 2x is. Here these two blocks or the spheres are connected by a string. A force F is acting on the string in the vertically upward direction at the midpoint. So the shape of the string changes, right? Now the total length of the string is 2a, that means this is a plus a, right? Half of the length is a. Now we have to find the acceleration of the blocks. See, the blocks are moving in the horizontal direction towards each other. Now when the separation is 2x, that means from the midpoint the distance is x. When the distance from the midpoint is x, you have to find the acceleration. But the tension is acting not in the direction of acceleration. So the tension is acting in this direction, but the blocks are moving in the horizontal direction, right? So we have to take the component of the tension force. Yes. Now let us consider this right angle triangle. So that hypotenuse is a, half the length of the string, and also half the distance here is x, and take this angle to be theta. Okay, it is a right angle triangle. Now we can find sin theta or cos theta, whichever is required. Now let us consider all the forces acting on this block, right? One of these blocks, right? Any one of the spheres, right? Because both these spheres will move with the same acceleration. Okay, at least the magnitude. Okay, now let us consider the horizontal component of the tension. The tension is acting in this direction. What is the horizontal component? That angle is theta. This is 90 minus theta. So on the block, so the tension force is the only force, right? Only the component of the tension in the horizontal direction. That is the only force acting on the block. So that means that is T sin theta, because that angle is cos theta with the vertical, with the horizontal sin theta. So T sin theta. That is the force. So that equals the mass times the acceleration. That acceleration is what we need to find. But sin theta and the tension are to be found. Okay, yes. Now what you do at the point A, at the point A, what are the forces acting? See, point A means only that small portion of that ring, right, that string. So that means that is mass 0, right? At that point, what is the force acting in the vertically upward direction? The vertically upward direction, the force F acts, and what are the forces acting in the vertically downward direction? So point A, only the vertical direction. F is acting in the vertically upward direction. So F, and the tension is acting in the vertically downward direction. Only the component of the tension. The angle is theta, the tension is in this direction, away from that point, in this direction tension. Component is T cos theta. So T cos theta. But also we have tension on this side, right? This also has the same component T cos theta plus T cos theta. So 2T cos theta we can write. So total force in the upward direction is F, and downward direction we have 2T cos theta. That's the total force acting at that point. Okay, that must be 0 because mass of that point is 0, right? So because it is just a small portion of the string, so that has mass 0. So that means, so this is one equation. So we can solve these two equations to get the value of the acceleration, right? That's all. So T, we have to eliminate T. So let us eliminate T. So how will you eliminate T? We can substitute here. So this gives you the value F minus 2 cos theta multiplied by T. So T can be substituted from this, right? So MA divided by sin theta. So that equals 0. Okay, so from this we can find the acceleration. So what is the acceleration? So that is, so this acceleration is F divided by 2m cos theta by sin theta, that is cot theta, and if you divide, so that will become tan theta. Okay, so that's also, this is the acceleration, but tan theta can be found from that right angle triangle, right? In that right angle triangle, tan theta is opposite side, right? Opposite side divided by the adjacent side, that can be found using Pythagoras theorem. So that is f divided by 2m multiplied by tan theta, opposite side, that is x, divided by the adjacent side. So that is using Pythagoras theorem, square root of a square minus x square, right? So that's all. So that is the required acceleration of these two blocks, right? So that's all. So fx divided by 2m root a square minus x square. So that is the answer. We have done some basic concepts of the tension force. We will continue with this tension force in the next class, getting this pulley block system into our discussion. Okay.